Welcome to a new session of network synthesis analysis. In today's class, we are going to learn about Foster Form 1 and Foster Form 2 for RL networks. Here you can see an example of Foster Form 1 for RL circuit. In one form that is impedance form and another one is in admittance form. So how we are going to frame these two forms we are going to see in this session. So let us start with the first example where impedance function is given by 2 times of s plus 1, s plus 3 divided by s plus 2 and s plus 6. This is a numerator and denominator polynomial. The numerator represents the zeros and the denominator represents the poles of the given impedance function. Okay, so identify the poles and zeros by equating the numerator equivalent to 0 and the denominator equivalent to 0. We are going to get the poles which are at s equal to -2 and s equal to -6. You can see from this polynomial z of s, whereas zeros are at -1 and -3. So if at all we plot this pole 0 plot, and we are going to observe that the lowest critical frequency is a 0, which may be at s is equal to 0. So you can see this is the pole 0 plot where you have on the real axis given by sigma, on the imaginary axis given by j omega, and arbitrarily let us choose the values from 0 to -8 on the negative real axis. Now just plot the poles and zeros over here. You can see -1 is a 0 which is near to this actually axis to 0, and then you have another 0 which is at -3. So this is how we plot the zeros on pole 0 plot. Now -2 is the pole at s equal to -2, which is on the real axis, and -6 over here, that is also on negative real axis. So this is a pole 0 plot diagram for the given impedance function. Okay, now here the lowest critical frequency is a 0, located at s is equal to -1, which is near to s is equal to 0. That is the catch over the RL circuit. So when you going to check the transfer function, what we say, we talk about the impedance function. The applying the initial partial fractions, we can get z of s in the terms of a naught and b naught. And if at all we obtain the value of a naught by partial fraction as -1/2 and b naught as -15/2, the residues are in negative sign. So when the negatives are in the negative sign, we have to take the partial fraction expansion, which is nothing but equation 1 is modified as zs by s. So this is the approach of Foster form 1 under RL realization. Now z of s by s, if at all we take the equation 1 in the modified form and in equation 2, we are going to get 2 times of s plus 1 and s plus 3 in the numerator, and s into s time s into s plus 2 and s plus 6 in the denominator. Now by actual partial fractions, I can get the z of s by s value in the equation form 3. Now let us calculate the a1 value. It is obtained here as 1/2. b1 it is 1/4, and c1 it is obtained to be 5/4. So if at all I substitute the values of a1, b1, c1 equation 3, I am getting equation 4 like this. But the actual notation of impedance function should be in terms of z of s. So I'll take this z of s and I'll take this denominator s on the right side of equation 4. So z of s is equal to 1/2 plus 1/4 s by s plus 2 plus 5/4 s by s plus 6. This is the equation what we have obtained for impedance function for RL circuits. Now Foster form 1 from equation 5 indicates the first value as the z0 value, or it is also treated as r0 value, and the next value of z1 we are treating as z1 of s, which is nothing but 1/4 s by s plus 2. Similarly, z2 of s we are treating as 5/4 s divided by s plus 6. Now this is the actual Foster form where you have a representation of R0, Z1s and Z2s in the series combination, you can see. And what is this Z1 of s and Z2 of s? That can be derived from the formula ZRL of s, which is equal to Ri of s whole divided by s plus Ri by Li. Now this is the representation of the impedance in terms of resistor in parallel with inductor. So, for example, we take Z1 of S here. So, let us treat the case as 1, and Z1 of S is equal to R1 of S by S plus R1 by L1, which is taking the similarity of 1 by 4 S by S plus 2. Now when you equate the terms, R1 is obtained to be 1 by 4 ohms and R1 by L1 is nothing but here it is 2. So with this I am going to get the value of L1 as 1 by 8 Henry. Similarly, we'll take the case 2 and we'll obtain the value of Z2. With that, we can easily get the value of R2, which is 5 by 4 ohms. And R2 by L2, here you can see it is 6. And L2 will be 5 by 24 Henries. Now, this we treat in equation as 8. Now, the Foster form representation of RL function, you can see over here, we have R0 in series with the parallel combination of L1 R1 and in the series combination of this parallel R2 L2. Now just we have to substitute the values of R0, R1 L1 and R2 L2, then we are going to get the series combination of parallel RL circuits. So if it all we substitute the values, this is how we get the Foster form 1 of the given RL function. I hope you have understood this approach. Now let us go with the Foster form 2. So we are treating the equation 1 and we are just taking y of s as the uh, inverse of this z of s function. So s plus 2, s plus 6 go to the numerator and denominator comes with the 2 times of s plus 1 and s plus 3. Now you see the numerator as well as the denominator, the degree of the polynomial is the same. So numerator degree and denominator degree are one and the same, that is s square. So modifying this equation 9 and it is obtained to be equation 10. Now you can solve this equation 10 by synthetic division. This is called as synthetic division, where we are going to take the value of the quotient as 1 by 2. Just you have to divide this s square by 2s square. You are going to get the quotient as 1 by 2. Now when you multiply 2s square with this 1 by 2, we are going to get s square, and 4s multiplied with 1 by 2 will give you the value as 4s, or 8s multiplied divided by 2, you are going to get 4s. Then 6 divided by 2, we are going to get the value as 3. Now taking the subtraction of this, we are going to get the value as 4s plus 9. Now you see we have the quotient as 1 by 2 and the remainder is 4s plus 9. So what we are going to do, y of s, we are going to take the value first this quotient as 1 by 2, then we are going to take this remainder 4s plus 9 divided by this actual the uh, divisible, that is the 2s square plus 8s plus 6. Now this can be further modified with the actual equation which is found with the 9, and we are going to treat this as equation 11. Now you see we have this y of s, it is treated in terms of y0 as the first Foster form value, and the next Foster form value as y1 of s, which is nothing but this particular polynomial. Now this y1 of s again can be solved with the help of partial fractions. So that is what we are going to do. We are going to take the value of this y1 of s with the partial fractions of a2 and b2. We'll try to find out the value of a2. Here a2 is obtained to be 5 by 4 and b2 is obtained to be 3 by 4. Now after finding this the value of a2 and b2, just substitute in the terms of y1 of s. So y1 of s is replaced by this value and that y1 of s is substituted over y of s. So overall y of s is equal to 1 by 2 plus 5 by 4 s plus 1 plus 3 by 4 s plus 3. Now again it has taken the form of Foster form 2 standard representation. Now the first value is y0. We are writing the value of y of s as y0, y1 of s and y2 of s. Now we can solve y1 of s in the terms of Foster form 2 as well as y2 of s with the formula yrl of s is equal to 1 by li whole divided by s plus ri by li. Just remember this formula. This keeps on changing with the different types of functions. That is, for RL function we have y of s formula is like this. The parallel combination leads to this formula. Now for y1 of s, we are just taking this 5 by 4 by s plus 1 and we are equating with this y1 of s, the standard form as 1 by l1 plus divided by s plus r1 by l1. So with this what we are going to get, we are going to get the value of r1 and l1 which is nothing but 4 by 5 Henry and 4 by 5 ohms, and case 2 we are taking this y2 of s and we are matching with 3 by 4 divided by s plus 3. Now with this we are going to get the value of r2 and l2, and once we obtain with L1, R1, L2 and R2, we are going to go with the Foster form 2 representation. So here you can see the admittance is taken as a parallel combination of series circuits. So y naught of s is the first value of y of s, y1 of s is treated as second value, and correspondingly the number of terms which are here present, that is taken in parallel combination. Now, when you substitute the values of RL, this is what you're going to get the Foster form 2 representation for Y, uh, Y matching, that is admittance matching parameters. Now, just take the values of R0 as 2. This is, you can see here we have 1 by 2, then R0 becomes as 2, just by putting the reciprocal values. Now you can see here we have L1 as 4 by 5 Henry. We obtained the value of R1 as 4 by 5 ohms, and L2 as 4 by 3 Henries, and R2 as 4 ohms. Now when we replace the values of this L1, R1, L2, R2 and R0, this is what we are going to get. Now you can see we have this kind of form which is known as Foster form 2, which is the parallel combination of series circuits. Now you can see this kind of things can be applied for different impedance forms, that is given by A, B, C and D. Just solve these values and comment in the chat box regarding the solution for these impedance functions. That's all for today's class. I hope you like this video. Please share among your friends and subscribe to the channel for the future notifications. Thank you.